Okay, so next talk is a regular presentation titled Identifying Potential Attack Scenarios in Complex Systems by Means of Provenance Graphs. The presentation is by Loic Robert. Are you a PhD student as well?
Yeah.
Yeah, a PhD student working with both Airbus company and LAAS-CNRS laboratory. I guess you get funding from Airbus, right? We need to say that. Oh, yeah, you're working with Eric. Sorry. And yes, the floor is yours. Thank you.
Okay, thanks. So thank you everyone for attending this presentation. I will be presenting my PhD work on identifying potential attack scenarios in complex systems, thanks to provenance graphs. So it's a work that has been done between LAAS-CNRS and Airbus with ANITI. By myself, Vincent Nicomette, Eric Lacombe, Marie-José Huguet, and Emmanuel Hebrard. So I'll split this presentation in 6 parts. So basically, first off, some context. Why are we doing this work? A little bit about a little bit of formalism on State-Expanded Provenance Graph to explain the structure. What problem do we still have with the structure and how to mitigate it? The toolchain we developed to implement our findings. Then an illustrative examples and some limitations and next steps. Oops. Okay, fine. So let's go on the context. So the work is being motivated by understanding how complex system works and how the information flows across a complex system. So what a complex system is, in our case, it's a single host with multiple long-lived process, some shared files, some inter-process communication, and some background activity. So basically, a lot of stuff is happening in the system. And the cybersecurity evaluator, so a pen tester on this system, wants to understand a bit more what his action trigger and given a target entity that he wants to join, what his actions are doing basically to this entity. So the evaluator has access to some functional executions of the system. He can execute the system and see what happens. He has potentially access to some implementation knowledge, like specifications. It can really be anything that helps him understand the system. And maybe also the program binaries, but it's not mandatory at all in this approach. But the evaluator does not have a confirmed attack scenario on the system. So basically, we are more in vulnerability research. We want to pen test the system than post-mortem analysis. And a main problem we have in complex systems is understanding how the information flows across shared resources. So basically on the right here, you see that multiple processes write to a shared file. Then another process reads from it, and we would like to understand where this information comes from. It's really the hard point that we call overlinking. We would like to better understand the information flow. So as I said, we have a single host with multiple processes that are communicating. We have the functional execution, some functional executions of the system. Our approach does not aim to replace already known techniques for understanding how information flows through a process, for example. It's really more about establishing a framework that the cybersecurity evaluator can use and a method to understand the complex system through iterative work. And it is designed to discover, design vulnerabilities. So when you have a lot of things happening, you can either watch if there are some runtime vulnerabilities in some of your processes, so it's really located, find some bugs. What we want to achieve is to find design vulnerabilities, so things communicating in an unexpected way, or at least the cybersecurity evaluator can reach some unexpected, can produce some unexpected behavior on the system. So the work is split in 3 big parts. That is capturing what happens in the system. So our idea is to make this capture minimal. We don't want to instrument the apps. We don't want this to work only on some specific hardware. We don't want to change the source code of the processes. Then from this capture, we will instantiate a model that we call the State-Expanded Provenance Graphs that I will explain just after that. And then the evaluator should be able to give more insights on how the system works or how maybe some processes work in order to give more information to the provenance model and be able to do some clever deductions. So about State-Expanded Provenance Graphs, basically, we view our system as 2 sets of entities. We have the processes that are doing some actions and the resources that are used by the processes, basically. Among those resources, you have 2 kinds of resources. The storage resources that read operation does not alter, so you can see it just as a regular file, for example. And the consumable resources which are mutated through a read operation. So you can see an example of that is a FIFO. When you read content from it, it's removed from the FIFO, so the resource is mutated. Our atomical observation unit in the system is an event. An event as a type, so you can differentiate those. It has an emitting process, so a given process only emits an event. It has a set of sources of information. So in the case of a read event, the file that is being read is a source of information. It has a destination of information. When you write to a file, it's a destination of information. And then some input and output values that can be of many kinds. So the event is the abstract unit. We instantiate it in our work through system calls. So the system calls can have some various input and output values. And then we call an execution trace a finite time order sequence of events. So we will be working on execution trace and how to determine from them how the information flows through the system. A problem with usual provenance graphs is that they don't track the state of the entities across the time. So we introduced a concept that is a state version for an entity. I'll spare you the formula because you don't want to read it now. Basically what it does is counting the number of times an entity has been a destination of information. So counting the number of times it received information. For all those times, it will create a state of this entity. And thanks to all states of all entities across the trace, we create the State-Expanded Provenance Graph, whose vertices are basically all the states of all the entities across the trace, and an edge represents the transition of information between the sources of information of the event and the destinations of information of the event. So on the bottom here, you can see some structure that is created in the State-Expanded Provenance Graph for read events. So you have the process A in the state N. When it reads from a resource X, the resource mutates as X, in this case, is a FIFO. So it's altered by the read operation. It gathers the information from X through a new state. As the read operation did have some parameters coming from A, so for example, the size to be read, the new state of X depends also on the previous state of the process. So here you can have an example. You have a trace on the bottom left that is basically just 12 events, read and write events. The source and destination of information. On the top left, you can see a classical provenance graph that is not of much help to understand the information flow. I mean, from X, with this structure, you're not able to see where the information really came from. It can come from A, B, C, and E. And the derived State-Expanded Provenance Graph from this trace that we will see have some interesting properties. So The point of a state-expanded provenance graph is to better inform on the information flow that is occurring in the system. So from its very own structure, we can say that an information flowed from X to Y, so entities X and Y, between events EJ and EK in the trace T, if there is a path in the state-expanded provenance graph between X at the time J and Y at the time K. So it's really abstract for you for the moment, I guess. What it means is that if I want to know where the information in X comes from, I have to look at every other entity state version that have a path to X to determine if it's possible or not for it to have flowed information to it. So in this graph, for example, we can see that any state in red cannot have transitioned information to X. So all those are eliminated from the provenance analysis, which is really convenient. This property should not be confused with this converse. The converse being, if there is a path in the state-expanded provenance graph, there is an information flow. It cannot be known. So it cannot be known because we don't have enough details to say if the information effectively transited or not. We know that structurally from the trace is possible, but we don't know if it really happened because we don't have, well, the process code. So basically, we cannot deduce that. And without further looking at the resources and how they got information and made them transit, we can neither deduce. So basically, we have two overlinking motifs that we have to mitigate. When the information flows through a resource, we have to better track this to understand where it comes from and where it goes. And intra-process overlinking, which is basically when a process gets some information and then forwards this information elsewhere, we have to better understand the logic inside of the process, obviously. So the idea is not to replace some well-known methods. For example, for understanding how a process transits information, we have a lot of methods, symbolic execution, taint analysis. Those are really specific, and our goal is not to do this analysis, but rather to provide some tools in order to express this knowledge. So in our two cases, as I was talking, there is the inter-process pruning, so basically understanding how information flows through a resource. So in this case, we have three events, two writes from A and B to X, and then C reads content from X. So if we don't know the semantics of the resource X, we cannot deduce how it stocks and then forwards information. So the idea is basically to have a simple model on how the resources work. So here I take the example of a FIFO. Each time there is a write to a FIFO, we create a model where there is the chunk associated to who wrote that chunk. And then each time we read data from this FIFO, we can know where this data came from. So we can mitigate all this overlinking. So here is an example. Still those three events. After the two first writes, I can know the state of my FIFO. So a block of size 5 with word and a block of size 5 with hello. If C reads 5 bytes, I can understand that this data only came from event E1. So this data only came from A. So by applying such models on the resources of my system, I can better understand how the information did flow through them. For the second case, so intra-process overlinking, I would like to express how a process works, basically. So it means that I want to express implementation details of the process. Just as I said earlier, there are some really good methods to do it. We don't want to replace those methods because they are actually pretty good. What we want is a way to express this knowledge rather than creating it. And for that, we need two tools that are the event pattern and the causal property. So the idea behind an event pattern is to characterize some kind of event. I wouldn't like to create a property that is a event 148, then creates event 152. I want to say that an event that is a write from this process on this resource has to be forwarded by an event that then writes somewhere else. So really larger scale description. So here is an example of an event pattern. Pi states that it matches events that are produced by process A that are read operations, and X is a source of information. So basically, this event pattern matches any event that is a read operation by A on X. With this larger scale description, I can create causal properties, which are used to express the knowledge of dependency or independency of events. So basically here the causal property has a process on which it describes the behavior. It has a source event pattern, a target event pattern. So this kind of event creates this kind of event. A mode that is either a dependency or independent. So this event always happens after this one, and the converse. And an alignment property that I will explain on the next slide. So thanks to those causal properties, I will be able to create asserted path in my provenance graph. So I will be able to know that some path really have to be really do forward information because I added this knowledge. So from this can get out three situations. Either a path is asserted, it is validated by some knowledge I put into the model. Either it's discarded, so it is, well, some knowledge that I put into the system says that it's not possible, or it's uncertain, and uncertain is not a bad word here. Uncertain means that the model doesn't have enough information, so it should point the cybersecurity evaluator into refining this knowledge in the system. So here is an example. The scenario is that the process A reads a file name in a FIFO, and then it opens that file. So for reads a file name in a FIFO, I have an event pattern that is a read operation in the FIFO called FIFO request. So Pi1 is read operation on a FIFO request. The second event pattern is just an open operation. And to express this knowledge, I can create a causal property that states that the process A first does a read operation, then opens a file. So those events are dependent one another. And the alignment constraint states some more information about the cross-event linkage. So basically here, the buffer that is read from the FIFO should contain the resource name. So it expresses the exact match in the data. So with those three constructs, so basically the reachability that I explained earlier, the inter-process refinements, and then the causal properties, we have a lot of tools to better understand the information flows across complex systems. So we built a toolchain for that. Well, yeah, it's a bit readable. So the idea is that we have two softwares. One that is in charge of observing what happens in a system. So the evaluator should use this software to launch the functional execution of the system, probe what happens. So here it's through eBPF probes. Then normalize some stuff so that it can be used later by an exploring application that will present the state-expanded provenance graph that will allow to input some causal properties, and basically that will allow the evaluator to iteratively understand the system better. So I'll give you now an illustrative example of how this can be used. So in this system, we have a bunch of clients that are communicating through a router. Basically, the clients are just exchanging messages. When the router gets a communication from a client, he logs that communication inside the log file. This log file is recurrently, based on the time, read by a log collector, and then the log collector produces a report. This system has a vulnerability. In fact, the client protocol lets a client state its own identity, so a client can spoof any other client. And in our scenario, there is a line in the report file that states that there is a client called 99 where it should never happen. So we would like to understand the information flow that occurred in our functional execution to get back to the client that tried to spoof the system, that tried to spoof another identity. In this system, we have a bunch of overlinking centers. Basically, the log collector process, we would like to understand a bit how it forwards information from the logs to the report file. It will be done through one single causal property that will express this knowledge. We would like to understand how information transits through the logs file. So basically, what is written in the log file, when the log collector collects this data, where did this data really came from? I mean, which state of the router did commute that data? And then another overlinking center on the router, so how the router works, how it transits information from a client to the logs file. For this, I'll give you a demo on how the app works. So here we are inside the app. It's really ugly. It's not vibe coded. So we first load the trace. We can see all the events that occurred in the system. If I go at the very end, it's once every event occurred. I can hide some entities that are not of interest for this study. So here we can see we have the three clients, the router, the log collector, and the files. And now the big ugly state-expanded provenance graph. That's basically we won't be using by hand. We just have to find this state. So here it's called goal, but it's the report file. I want to find that point in the report file where I have this spoofed identity. And now I would like to understand where did this line, this content in the report file comes from. So without further information, it's not useful at all. Basically everything in the system could have flu information to there. Some states are still gray because they are not reachable. So with simple reachability, we can do nothing basically. But we see that what is written in the report file contains 3939. This is the exa for ASCII 99, which the client state is. So we'll be creating some event patterns to express this event of writing 99 in the report file and the log collector reading from the logs file, and then create a causal property on the log collector. And we can see that if we do provenance analysis again, we can now get back first off to the log collector state that did read from the logs file, and with inter-process analysis through the logs file back to the router that at the point the router transits this message. So from the router here, we are still blocked because we don't know how the router transits something he receives from a client to the logs file. It's still a behavior to express. Behavior that we express knowing a little bit a little bit more about the client to router protocol. So basically we create another causal property. The idea is to express basically how the router works. We don't have to state it all, but we just have to get a discriminating factor between the read operation and the write operation. If I do provenance analysis again, I see that I can get back to the client. In fact, that did do the spoofing, the faulty operation. And I can see in the message he transited that indeed there is 630000. 63 is the ASCII for base 10 99. So this state of the client really did transit the message 99. So thanks to those causal properties, I have a clear causal chain of from the report file to the faulty client with just two properties. So basically, I didn't have to model all my system. I just had to model a little bit of how those processes work. Okay, perfect. So in the provenance graph we saw, it's quite small. It's not a so complex system, but for exemplification's sake, it's not too bad. We can see that we had 1,700 events. So the state-expanded provenance graph had twice as much nodes, 4 times as much edge. So the scaling is not too bad as well. It built pretty quickly, so it was 14 milliseconds here. From the first query, we had 2,700 states, which was clearly completely useless. We could not get anything from it. But after just 2 properties, we could get 20 asserted states. 20 states are clearly auditable by a cybersecurity evaluator, so he can just investigate the causal chain and know what happened. And the query time is also pretty small. I mean, 19 milliseconds. It allows the evaluator to iteratively work with the tool. We did some tests on bigger systems. So basically here, instead of five clients, there was 50. And we saw that the build time and the query time just did grow linearly, so it was fine. Still under the second for a very big system, so still it can really work in an iterative way. About limitations and future work, for now, the main limitation is clearly that we won't find a vulnerability in a single trace. The idea is to integrate this process in the Airbus software producing pipeline. So when you produce a system, you first do functional tests on it. By instrumenting those functional tests, we can gather many traces and understand what happened on those functional tests. It's really, really unlikely that we will find a design vulnerability inside one single test case. Or else the system is really poorly coded. So the idea is to gather many test cases, many execution traces, and be able to combine them to uncover new behaviors. Also, just like I stated, the causal properties are just a way to express the knowledge. We could completely automate this process of producing the knowledge. Thanks to taint analysis or symbolic execution, we could state that yes, this event always happens after this event because they are in the same basic block or things like so. So thanks for listening, and you can find all the tools on my GitHub.
Thanks. We have time for one or two questions.
Thank you for the talk. I was wondering how do you, so you're doing provenance graph, how do you define the starting point of the analysis is an event and you want to know what are the causes of this event? How do you define the, why did you choose to identify the specific provenance of a given event? How do you choose the initial event that starts your analysis?
Yeah. So the idea is you want to do a steady. You have some invariants in the system that you would like them to hold. For example, this user should not be able, by any information flow, to modify this resource. So basically, any thing that this user does should not alter this resource. So this resource is the resource of interest, and you would like a write to it. So that's the event that you would monitor, never to come from an action from this user, for example. So some assets of interest where you would like to control or at least to audit where the information that does trigger this event come from.
Hey, one.
Hey.
Hey.
So I was wondering, so you're trying to find issues by analyzing some logs, whether where I come from. So I was working with SE Linux recently, and in SE Linux there is a audit to allow, which the purpose is to collect the log and add special rules to allow the systems that are designed. And you can also identify what is not supposed to happen. But it only works if you have every functionality that works. So that are triggered. You need to go through every path in the control flow of the programs of the systems. So do you plan to mix that with fuzzing or something else to exacerbate all those paths, or what is the way to make sure that all the paths in the execution paths in the system are triggered?
Yeah, it's a really important question. The question is basically about how do I ensure that the execution traces I work from are relevant? How am I sure that they cover enough of the system behavior? And it's actually really important because in our setup, as I said, we plan to get the execution traces from the functional tests. So it's out of the scope of what we do, finding good setups for getting relevant execution traces. But we we do think that the functional test should be able to cover enough of what the system is capable to do. So we really rely on the fact that the functional tests are actually good. Yeah, it's the way to guess the coverage is good enough.
We are a little late, so we have to stop here. Thank you. Thank you. We have to switch to next.